So in this problem we have this peg P being pushed along this path by this rotating rod here. So this rod is the one that drives this peg through this path. So we have the equation of this path that we take here, and they want to know the radial and transverse components of the peg's acceleration at the very instant that the peg's at this location. And they also tell us our angular speed and our angular acceleration. So here's my peg. We know that currently our angle is 45 degrees, otherwise known as pi over 4. I'll just keep it in radians, because I know that theta and theta dot and theta double dot, it's always safer if you keep it in radians. Some equations, like s is equal to r theta, they work off of radians, so you have to put in radians for that theta there. So it's always safer to keep it in terms of radians. So my theta axis, that transverse axis, will be this one. It's always 90 degrees to my radius r. And it's always in the direction of increasing angle theta. And I also have my radial axis. And I know that this object will have some acceleration, and maybe this acceleration is this way, but whatever way the acceleration is, I know I can split it into a radial component, AR, and a transverse component, A theta. And the equations for these two acceleration components are here. And we already know that angular speed is 2 radians per second, and the angular acceleration is 4 radians per second squared. So we already know we're already beginning to craft some of this equation together. So here I got a 4, here I got a 2, and here is a 2. Well, I see my unknowns. Probably the easiest unknown to start with is r. We can easily figure that out because we know the equation that this red particle takes. So at the instant that our angle is pi over 4, we know that the r will be 2.2. So we may want to get r dot next. Don't forget, r dot is just really the speed at which that radius is changing. As our particle is traveling, you can tell that those green r's are getting bigger, bigger, and bigger. At least in this region. You know, it all depends on what region we're really curious about. We're curious about this region right here. So who knows if my picture is really drawn correctly. It looks like, if you really look at it, it looks like these r lines will be getting a tad bit longer as our particle travels. But again, I'll let the math tell me here. So I want to compute my derivative. So I'll take the derivative of this equation, and I'll end up with the derivative of r with respect to t, how fast that r is changing as time changes. Now my derivative here, I have to be a bit careful. You always got to watch out for chain rule. Chain rule is really the most important derivative scale you'll ever learn. It's not going to be simply e to the theta, because we're taking the derivative with respect to t, not theta. And we have to realize that theta changes with time. You might even imagine that there's some equation in there in which you plug in a t and you get a theta. There's some equation out there that governs exactly how this angle is changing with time, and it's this equation that is in here. And you might also think, it all depends on how you think of chain rule, but what we have here is an equation where you put in theta and you get r. But likewise, there's an equation where you put in a t and you get a theta. So if I want to calculate the derivative of r with respect to t, what I have to do is the derivative of r with respect to theta, times the derivative of theta with respect to t. So it's chain rule, however you think of chain rule. So here's my derivative of r with respect to theta. Now I got to multiply this by the derivative of theta with respect to t. And I don't know what this is. I don't have any equation that I can actually derive. So all I can write here is the derivative of theta with respect to t. And of course, just recognize that this is what theta dot is. They're just two different symbols that mean the exact same thing. And of course we know that theta dot is 2. And we also know that our current angle at this moment is pi over 4. So if we do this calculation, we can figure out our r dot. That'll be a 4.39. So we have our r dot over here, 4.39. Last thing we need is r double dot, the derivative of the derivative. So here we have this equation that we just came up with, e to the theta times theta dot. We have to take the derivative of this again. So let's do that. We got to be really careful when we're doing that. We have product rule going on. We have two equations of time getting multiplied by each other. And just remember, we're taking the derivative of this whole thing with respect to time. We want to see how our radial speed, you might say, changes with time. So really, I want to see how this whole thing changes with time, so I've got to take the derivative with respect to time. Now both of these things are functions of time, because as we know, theta changes with time. That's actually pretty obvious. As this particle travels, that angle definitely changes. Now, does our angular speed change with time? Well, look at this particle moving. As we can see, it's moving really with the constant speed around this circle. So this is a case where, no, this would be a 0. This doesn't change with time, but as we can see here, they're giving us an acceleration, an angular acceleration. So apparently this quantity is a variable. It changes with time. So therefore I really got to go through my product rule steps here. Derivative of the e is going to be e theta times theta dot because of chain rule. Derivative of the theta dot is really just theta double dot, the derivative of the derivative. So doing my product rule steps here, it's going to be my first equation times the derivative of my second equation plus my second equation times the derivative of my first equation. And I have a value for each one of these. I got pi over 4 for my angle. Theta dot I know to be 2. And even theta double dot here I know to be 4. So if we bring all that math together, we'll figure out our r double dot. And we'll get a 17.54. My guess would be this would be in meters per second squared. So this is 17.54. So now I have all of my unknowns known here for these equations. So I can do the math. And I'll figure out that my transverse component for acceleration will be a 26.4 if I round up. And for my radial component, I'll get an 8.74. Now both are positive, which means both of these components here are in their positive axes. Remember, these are components, so to find my true acceleration, I have to add these components. And because these are vectors, I add using the tip-to-tail method. And of course, if I wanted to find out how much that acceleration is, I would do the sum of the squares of these components and then the Pythagorean theorem of that. Because again, this is just a right triangle situation up here. And I would get a 27.81. So I got my two acceleration components, got my acceleration itself. So that's this problem. So just keep in mind these equations for the acceleration components. Definitely don't forget your derivative techniques, product rule, and more importantly, chain rule, because derivatives play a huge part in dynamics. So, hope everything made sense. Feel free to ask any questions you may have in the comments.